And welcome back to our last lesson on geometry. In this lesson, we're going to be taking a look at the volume and surface area of pyramids and cones. Much like our previous lesson on prisms and cylinders, a cylinder is just a fancy name for a prism that happens to be circular. And as it turns out, a cone is just a fancy name for a pyramid that happens to have a circular end. Again, for whatever reason, a lot of our circle related stuff gets different names, even though it's the exact same. For instance, circumference is really just a perimeter for a circle. Anyway, I've already filled in the table on this one, mostly because I didn't want to have to try and accurately draw these to make them look right for you. But I am going to kind of go through them really quickly. Just to be clear, because this looks like it's kind of a weird picture. This is the base here, and there is one variable actually not listed on here. We have an L, which is actually going to be called our slant height. And then we actually have the real height, which would go from the middle of the bottom to the peak. Actually, you know what? I'm going to make that dotted. Hopefully that'll make it a little bit clearer. And it will meet the bottom at a right angle, and that's going to be our actual height. So height would be if you measured from the bottom to the top. Slant height is going to be a little bit longer. It's if you're measuring from the middle of one of the sides to the top along a diagonal. So we're going to see this when we go to some examples, but essentially that's going to be the hypotenuse of a triangle that has a height h and a width equal to half the, well, equal to the middle of the bottom shape to its outer edge. Now, as far as the volume goes, it doesn't matter what kind of pyramid you have. So for instance, in this picture here, I have a square-based pyramid, or at least looks square-based. It might be rectangular. I could do a pentagon base, a hexagon base, an octagon base, or whatever. It doesn't really matter. They'll always have the same volume. The volume will always be the area of the base times the height, and then divide by 3. So it turns out that if we could do anything with prisms, the pyramid equivalent of it, where we come to a point on the opposite side instead of an identical shape on the opposite side, is just going to be 1/3 of that volume. Now the surface area becomes a little bit more complicated depending on the shape of the base. If the base has got, basically it's like a quadrilateral where all sides are different lengths, then we have to kind of calculate each of the triangular pieces separately. So we're only going to deal with the equation for regular pyramid bases. So basically anything that's a regular polygon. And I'll just scroll down a little bit so I can talk about that for a moment. Regular polygons are just any two-dimensional shape where all sides are the same length and all angles are identical. So there's a regular triangle, which is also called an equilateral triangle. A regular quadrilateral is just a square. Rectangle could be oblong. That doesn't count as regular. Pentagon, hexagon, and then so on, all the others. I'm not going to bother listing them all. You don't need to know the names. You just to be aware that regular polygons have all sides equal. And similar to yesterday, I'm actually going to go down and just show you the skins for these. Okay. So the skin for a, in this case, a square-based pyramid is going to be a square. That's the bottom. And then you're going to have 4 identical triangles. The height on each of the two-dimensional triangles is equal to the slant height of the pyramid itself. And then obviously its base is whatever the side length of the square is. And I think you can imagine that if the base is a weird shape, each of the triangles coming off it like that are going to be different. If we had a pentagon base, so there were 5-sided base, then we'd have 5 triangles coming off it. And if we had an octagonal base, we had 8 sides, we'd have 8 triangles coming off it, and et cetera, et cetera, et cetera. So the geometry is much easier if we deal with regular. If they're not regular, you can do them. It just means you have to work out all of the triangles individually, which can be a little bit tedious. So we're not going to bother doing that in this course. Going back up, the surface area is the area of the base times the area of the 4 triangles together. The 4 triangles together are basically going to be equal to half of a long rectangle. So we're going to be looking at the perimeter of the base times the, in this case, slant height, because we're dealing with the slant height, whereas in the previous lesson we dealt with perimeter of the base times height. The slant height will be our triangles, and then the division by 2 is because each side is a triangle, so basically base times height divided by 2. And instead of treating them as 4 separate triangles, I'm just putting down the perimeter. That basically says 4 times the side length, so there's 4 triangles, each of which is base times length divided by 2. For the cone, you'll notice that the volume equation is essentially the same as the volume equation for a pyramid. The only difference is we know the area of the base is pi r squared because it's a circle, so it's pi r squared h divided by 3. And then similarly, when we compare this, the area of the base is pi r squared. And the other part, the lateral piece that we're going to get, which is easier to explain in the net below, is equal to pi rl. Now that one I actually will kind of do just a really quick little calculation on so you can see why that's true. First of all, I think you can see without too much trouble that this piece here, the lateral piece, is part of a circle. I'm going to try not to make too much of a mess here, but it's part of a big circle there. So it looks something like that. And now that I've made the mess, I'm going to get rid of it, or try to. Come on, erase, erase, erase. Okay, so that's part of a big circle. Now its actual area, that big whole circle, would be pi r squared, but in this case the radius of this is L, so this would be pi L squared. But it's not obviously a whole circle. It's only a little piece of a whole circle. In this case, it looks like it might be around a third of the circle, but I mean, it could be any fraction depending on how tall the cone is relative to the circular base on it. But what I will point out is that the circumference of this is 2 pi r, which means that's going to be the same as this length here, because that has to wrap around the circular base. And this is going to be 2 pi r as well. So the area of the whole circle is pi r squared, but we have to multiply that by the fraction of the circle that we have. So if it was a quarter of a circle, we'd multiply it by a quarter. If it was a half a circle, we'd multiply it by a half. In this case, I don't know the exact ratio, but I do know that the arc length, or the distance basically around that we have, is 2 pi r. And I know that the entire circumference of the big circle is 2 pi times its radius, which is L. So what I can do there is cancel out the 2 pi's, and I can cancel out the L on the bottom with one of the L's on the top. And what I'm left with is pi times L times R, or pi RL. And that's where the pi RL in that equation comes from. So this is the area of the circular bottom, the pi r squared, and the pi RL is the cone piece, which is basically part of a larger circle with radius L. Okay, either way, you've got the formulas there that you can use. Let's go down and jump into just a couple of examples. So here we have a picture of a very fictitious geometric ice cream cone, which happens to be a cone with exactly half a sphere of ice cream on top of it. I know that's not particularly realistic, but in mathematical modeling, really complex shapes are usually hard to do, so we approximate them with basic shapes. In this case, like I said, a cone and half of a sphere. So what is the area of the cone? Well, for this purpose, I'm just going to say we're referring to the cone itself, not the cone with the ice cream in it. So we're just trying to figure out what the area is of this piece. All right, in order to do that, I look at my equation, and my equation for the surface area of a cone is pi r squared plus pi RL. And here's the thing, there is no pi r squared piece to it. Remember that that's the area of the circular base. Well, the cone doesn't have a cap on it. That's where the ice cream goes in. So this is where we have to understand where the pieces of the equations come from, so we know which to include and which not to include. Because like I said, our cone will not have a sealed end on it. It's just going to be open so that ice cream can go in. So we're really only dealing with the lateral part, the pi RL. In this case, we know that pi is pi. It's not a variable, it's a constant. We know the radius of the cone is 3. And we know that the slant height is 10. So that's just equal to 30 pi, or what does that work out to be? 94.2 centimeters squared. So I don't know if anyone's been to an ice cream shop and watched them make waffle cones, where they basically take a piece of waffle and just wrap it into a circle. So it's basically that would need to be the area of the piece that would be needed to make it. And of course, in real life, they actually overlap and it's a little bit larger than that. But again, in math, we're just doing some approximation stuff here. All right, if the cone is full of ice cream, what volume of ice cream is there? Now, the question's a little bit vague here. We're going to assume that the cone is full of ice cream and that there is ice cream on top of the cone in the half sphere. So let's do the total for that. The volume for the cone part is going to be pi r squared h over 3. By the way, I think I used capital L for h in the last lesson. Don't get too caught up on it. It's, again, just variables. Plus, we're also going to have the half sphere. The equation for the area of a sphere is 4 pi r cubed over 3. And I'm going to put a half in front of that rather than try and do a fraction over a fraction where I divide that by 2. So we have half of a sphere. Okay, I can start plugging in variables at this point, except that I'm actually missing one. I have the r, that one's easy enough, but I don't have h. So what I'm going to do is go back over to my diagram and just try and draw a cross section of the cone, or at least half of the cone, because I know the cone has a radius of 3 and I know it has a slant height of 10. So it's going to have an actual height over here of h. And luckily, once I'm there, I can fairly easily do Pythagorean theorem and say that h squared plus 3 squared equals 10 squared. H squared plus 9 equals 100. H squared equals 91. And then in my calculator, the square root of 91 is 9.5-ish to 1 decimal place. Okay, now we'll fly back over to our equation and plug in pi times radius squared, and radius is 3, times 9.5, all divided by 3. And on this, I'm just going to do a little bit of simplification. We got a 4 on the top and a 1/2 in front, so that's just going to become 2 pi r cubed, and r is 3, divided by 3. So the 1/2 multiplied by the 4 to give the 2. We could have just left it all there and done it the next step, but either way. Here, I'm going to do another shortcut actually on both of them, because by coincidence, there's a 3 on the bottom and the radius was 3. So that simplifies things a little bit for us. First, I don't know why I keep doing this. I put an equal sign, should be a plus. Okay, so our first term is pi times 3 times 9.5 is 89.5. And our second one is 2 times pi times 3 squared, which is 56.5. Yeah, 56.5. So 56.5 plus the 89.5 gives us a total of around 146. And that would be centimeters cubed. Okay, so that's roughly the amount of ice cream. And again, I'll remind you, a centimeter cubed is also a milliliter. So 146 milliliters of ice cream. All right, the next one we're going to do is just find the volume and surface area of the pyramid shown. Volume, that one's not too tricky. That's the area of the base, which in this case is 6 squared, times the height. Now, unfortunately, if you look carefully at that diagram, the 10 is measuring the length of that dotted line, but it's going from the middle of a side to the top, not the middle of the base to the top, which means that that's actually the slant height, L. So I'm going to draw a little diagram under here. And I know the slant height is L. And since the bottom has a base length of 6, it's going to be 3 to get to the middle of it. And then it would be 3 more if we wanted to do the rest of that triangle, but we don't. So to find the height, h squared plus 3 squared equals 10 squared. And I did not do this on purpose, I swear. But apparently that's exactly the same as the cone that we just did above, which means that h is, what did we say it was, 9.5? Yeah, 9.5. All right, so h equals 9.5. That never happens, those weird coincidences. Okay, so back up here, area of base times height. That would be for a prism, but for a pyramid, I take the exact same thing and divide by 3. All right, so 6 squared times 9.5 divided by 3 equals 114. And that would be in centimeters cubed. And then to find the area, this is going to be equal to the area of the bottom, which is just 6 squared. And I could go back and actually look at the equation, but I'm going to do it slightly differently. I'm going to say there's 4 triangles, like here's a triangle. There's 4 triangles, and each of them is base times height divided by 2, which is 6 times 10. 10 is the height. It's the slant height of the pyramid, but it's the height of the triangular side if I actually just look at the triangle. So base times height divided by 2. And if I use the equation that I actually gave in the lesson at the top there, that was perimeter times height divided by 2. But the perimeter of the square base is just 4 times 6. So you're going to get the same thing. My point is I very seldom look back at the original equations for these and just treat them as it's a 5-sided object. One's a square, 4 are identical triangles. Just find the area of the square and the triangle and you're done. Okay, so that gives us 36 plus, I should be able to do that one in my head. 4 times 6 is 24, divided by 2 is 12, times 10 is 120. So 156 centimeters squared. All right, so what looked like a fairly big question, actually pretty straightforward. We did have to use a little bit of our trigonometry to find the unknown height given the slant height. And in some questions, you may be given the height, need to find the slant height. Depends on the situation. But once you're there, volume is just a fairly straightforward equation, and surface area is just break the shape into its different two-dimensional shapes and find the area of each, and you're good to go. All right, as always, there are some practice problems to try at the end. Give those a shot, see how it goes. If you need help, contact me. Otherwise, fantastic. Have a good day, and I would say I'll see you in the next lesson, but this is kind of our last interactive lesson for the course. We do have one more topic to continue after this. However, that topic is an ISU, which means that there really aren't lessons. It's all online interactive. So yeah, good luck with that, and we'll talk to you when we talk to you. Have a great day.